Hello. So now we will see the editorial for the question. बहुत तेज हो रहे हो हैं from Convex 2.4. So in this problem, you are given a tree on n nodes where the ith node has weight wi. So and these are integer weights, and so you are asked to find the vertex v such that this quantity, that is summation wi times dvi. So here by dvi we mean the distance between vertex v and I. So this product wi into dvi summation over all vertices is maximized, right? So this is some kind of a notion of a center, but here we are trying to maximize this weighted distances. So it is not exactly the center of a tree. So just for clarity, here distance vi. So in a tree, as we know, so this distance vi denotes the number of edges between the on the simple path between vertex v and I. And as we know, it's a tree, so such a simple path is unique. So this distance is a fixed number. So now we are asked to find this v which maximizes this quantity. And also, if there are multiple such v's which have the same maximum quantity, we are asked to give the vertex with a minimum index in the tree. So as the vertices are labeled from 1, 2 and so on till n, so we need to find the one which has a minimum index. So now let us see an example. So the sample test is given was this tree where the weights are 1, 2, 3, 4. So in this case, if you compute the value, this value, keeping v equal to 1, so you get for v equal to 1 the answer is 13. For 2 it is 19. So here so this first number is the weight of that vertex, and this is the distance. So distance from 1 to 1 is 0, from 1 to 2 is 1, from 1 to 3 is 1, and from 1 to 4 is 2. That means this part. So in a similar way, if you compute all these values, so you see that when you select v equal to 2, you get the maximum value of 19. So the answer here is 2. So this problem will be solved. We will be solving using dynamic programming on trees with the rerouting technique. So let us dive into the solution. So let the for just so initially let the tree be rooted at 1, the vertex 1. So now let us try to solve a simpler problem, a different problem here. So let us say v is some vertex in the tree, in this rooted tree. Let us try to find the answer, that is this summation wu into dvu, where u belongs to just a subtree of v. So here you have some tree over here. So what I'm trying to do is for this vertex v, I'm trying to find its answer just inside the subtree. Okay, so just considering the vertices in this subtree, what is this value? So let us we'll do this using dynamic programming. So let dpv denote this value that we're trying to find in the subtree, and let sum of v denote the summation of wu, the weights, summation of weights of all vertices in this subtree. Okay, for any such vertex. Now let us consider a vertex u in t1. So this u can be somewhere here, let us say inside this tree. Okay, so now if I want to find the distance between v and u1, so if you note, the path always has to pass through c. So it has to pass through c, and it might go somehow and it reaches u here, but whatever it is, it has to pass through c1, right? So now if I want to compute this value of wu into d into distance of vu, you can divide it as distance of v to c1 plus distance of c1 to u, right? But distance to v to c1 is just 1 because there is just one edge over here, right? So hence this value is 1, so we get something like wu plus wu into distance of c1, right? So now let us take the summation over all such vertices u belong to t1, and that includes even c1. Okay, so summation of all these uh, distances with this weighted distances will, based on this formula, will give us summation u belong to t1 wu plus summation u belong to t1 wu into dc1, right? And this is nothing but sum c1 as we defined, and this is nothing but dpc1 as we defined, right? So now finally dp of v will be for summation over all the children of v, sum of c plus dp of c, and sum of v will be summation over all the children of v, sum of c. So this values now can be computed in a single DFS just by running one DFS. We can compute these DP values using a standard DP algorithm on trees, right? So standard traversal, depth first traversal, you can update these values of DP and sum simultaneously, and you get all of these DP values. So now we have essentially solved this problem. Now let us go back to our original problem. Our original problem required that we take the distances with all vertices for every vertex. Now, so let answer of v be the answer that we require, the final answer that we require. That is the summation of weighted distances with all vertices, where we selected as a vertex, center vertex. So now, if you observe, as the tree was rooted at 1, answer of 1 is exactly dp of 1 because all the vertices in the tree are present in the subtree at 1, right? So hence, the root of the tree gets the final answer directly. So this is an observation. So now we can essentially root the tree at all vertices and run this algorithm. This is one possible direction. So if you do it that way, you can just take the value at the root and that will be the answer for that vertex. But this is inefficient because you have to run a one DFS for all vertices, so it becomes order n square. But that won't run for the given constraints. So now we will see a very elegant trick called rerouting, the rerouting technique. So over here, let us say this is a given tree. So 1 is the root of the tree for now, and 2 is one of its child, and this is the remaining part. So here 1 can have maybe many children, and this can continue, right? And 2 is one particular child, and this is its subtree, right? So the rerouting technique says that so what you do is you try to make now 2 as the root of the tree. So if you make 2 as a root of the tree, just hold 2 and pull it up, so you get something like this. So now 1 is one of its child, and now 2 can have many child in its own subtree, but 1 is one of its children now. So in a very abstract sense, you kind of can do this operation in order one time, but we will see what do we mean by this abstract sense, what exactly is that. So now if 2 is a root, then basically you can compute the answer at 2. Similarly, you can repeat this algorithm for the children of 2 and then for all children of 1 and basically for every vertex in the tree. So what do we mean exactly by making 2 as a new root? So let us do the following. Let us assume total sum as a summation of weights of all vertices. Now what I do is dp of 1 initially was exactly answer 1. So now what I do is I change its value. So from dp of 1, I remove the contribution from the subtree of 2. Okay. So what I have is this 2, and I have the subtree, and I have this remaining part here. I'm trying to remove the contribution from all vertices in this part of the tree, right? And what is that contribution? That would be dp of 2 plus sum of 2, right? That was exactly the value that was being added from this child towards 1. So I remove that contribution. So now dp of 1 just has a value from this part of the tree, right? Now if I make 2 as a root over here, so I have something like this 2 and then 1, and then I have a subtree here. So dp of 1 is basically telling I have the value at this subtree, and now I update the value of dp of 2 as following. I'll make dp of 2 as dp of 2 plus the contribution from subtree 1 in this new tree, and that is exactly dp of 1 plus the total sum in the subtree, and that total sum is nothing but the actual total weight minus the weights in the subtree, right? So now my new dp of 2 value will be dp of 2 plus this quantity, And now essentially my answer of 2 will be dp of 2, right? So now you can see in an abstract sense 2 became the root of the tree and it got the value of answer of 2 in order one time, right? Now you can continue doing this in a depth first search fashion again. So that means, by that I mean, go to the children of 2. So let us take a child of 2 and now make this child as a root. So as we already have the final answer here, you can do this same calculations for this vertex. Similarly, keep going downwards and compute it for all vertices in the subtree of 2. So once all of those values are calculated, so we'll return back to 2. That means I have computed answer values for all vertices in the subtree of 2. Now we need to make 1 as a root again. And why do we have to do that? Because we just computed the values for one child of 1. But 1 can have multiple children. So we need to go to the subtrees of those children also. So now I need to make 1 the root again. And how do I do that? Just return the values, whatever we did. So I added this value before. I subtracted again here, and as I subtracted this value before, I'll add it back again. So I'll go back to the original values. So by that I mean dp of 2 will be answer of 2 minus whatever contribution I added before, and now I make 1 as a root, and to 1 I add back the contribution of subtree of 2. So now all the dp values go back to their original values, and answer is storing the answer separately. So I hope you got what this rerouting technique means. So I'm making every vertex in an abstract sense the root, and I calculate the value based on the dp values. Fine. Now let us see the final implementation. So let us just get through all of these input stuff. So you take the number of test cases, run it that many times, take n as the input, and the weights of the vertices of the input and the edges. So now adj is the adjacency list of the tree. So now dp will store my dp values, and also to optimize in space, my dp will also store the final answer also, and we will see how do we do that. Why don't we need a separate array to store those? And next sum will denote the sum of weight in the subtree of that vertex, and visited is just a visited array. And now we call two different dfs's. So as you can see, the first part, uh, this required one DFS, and now this part also requires a second DFS to solve it. In a single DFS, you can get the new value, get the answer values. Fine. So we call this two DFS algorithms. We will see what those are, and then once we get the answer values, I just uh, find the vertex which has a maximum value, but it's just by running a loop. Fine. So let's see the Dfs One algorithm, the first DFS, which computes the DP values, the first step that we saw, right? The DP values. And that is a simple DFS. You just run the DFS, uh, initially make sum of u as WU, and make the vertex U visited. And now for every non-visited vertex in the adjacency of U, I call DFS1 on it, and whatever was the value of sum that was calculated for that child, I will add it to U, and also the DP value as DP of V plus sum of V, as we saw the update previously. And now to compute the answer values, we have the second DP, a second DFS. So in this DFS, what we do is, similarly we go to the non-visited children of this vertex U, and first I remove the contribution of this child V from U, and I add the contribution of U to V. So now V becomes a root, and I call DFS2. So now if you notice, DP of V is going to is storing my answer of V also, right? Once I call the DFS and I return, as now my DP is going to store even the answer values. You can see DP of U is no more storing the answer value because I removed the contribution of this part. So I add that contribution back. So this is by again a simple arithmetic. We can just add that contribution back. So now this DP value itself is going to show the answer values. I hope this is clear. And finally, just going over the time complexity ones. So first DFS takes order in time. Second DFS takes order n time. So the overall time complexity is number of test cases into n. So it's order t into n. Thank you.